This week's episodes were brought to you by the generous support of Andrew Henninger. Hey folks, Quilly18 here, and welcome to another episode of our Unity base building game tutorial, codenamed Project Porcupine. We are going to continue to work on pathfinding today. Last episode, we very nearly finished our implementation of the world graph, and because I want to make sure that I've got the entire pathfinding system done in a sort of cohesive manner here, I'm recording all of these pathfinding episodes sort of back to back, which means if you guys did find some sort of issue or glitch or just a failed optimization in the code to date, which would not surprise me in any way whatsoever, I apologize for the fact that I won't be able to respond to it quite yet. Hopefully, if there is an issue, I'll be able to figure it out relatively quickly and painlessly, and otherwise I will try to get back to you once they're all there. But I want to make sure the whole system works before I put up the first of these videos, because otherwise that would be really bad to have to backtrack too much. Okay. So the last thing we have to do in our graph is we have to go and create the edges between neighboring nodes. And we need a function that quickly or easily, very conveniently, might not be all that quick, but conveniently returns all the neighbors of a tile over here. And what I'm going to do, we have in our... We've had to figure out some amount of neighborness in, say, our furniture sprite controller over here, because right over here, for example, we are checking to see if the neighbors of our current tile is another object of the same type for walls, for example, because they link up, they hook up to each other and change their graphics. And then, we do a little check here. So we just get the tiles one at a time and then go through there. I guess that code will probably stay here. We could do some sort of neighbor code, but let's assume we're going to stick it there. We're going to do something relatively similar in tile. I'm not going to pretend that it's going to be specifically optimized, but it will do okay. So let's create a function. Oh yeah, we have all this commented out code, which I should probably clean up at this point. It's been in a couple of versions of our files at this point. So let's go ahead and do dat, and there we go. So we've got a funky little function over here, but we're all right. Okay, so that's two neighbors, two tiles are adjacent. But I want something else which does something like public tile get neighbors. Right? It returns an array of neighboring tiles. And we're going to put a Boolean here. It says diagonal OK. And we'll have it default to false. So it's going to return a list of those. Or not a list, it's going to return an array. And we can figure out the array size very easily. Well, do we? As long as we're willing to accept that some of the array positions could be null, then yes. The array size would be, or if the map loops, but I don't think we want the map to loop around from like north to south. The array size, assuming there are no diagonals, the array would be 4, or if there are diagonals, the array size will be 8. I just say, like, if we're the very topmost tile, then we don't have a neighbor above us. Therefore, technically, we only have 3 neighbors. Do we return an array of 3, or do we return an array of 4 with a spot that's a null? I'm going to say we return an array of 4 with a spot that's a null, and then the rest of our code will have to check for that. I guess that's just going to have to be the way that it is. I mean we could create a differently sized array, or we could use the list or whatever. That's fine. I could return an array of size 3, but then like which position is which. So yeah, I think what we're going to do. Oh, wow, there's a lot of different ways to do this, especially when you think about the diagonals. What's the order going to be? All right, let's say if diag_OK is false. Again, you could do the exclamation mark for a not, but let's do it this way. So we're going to create, there's going to be an array here. So this is going to be an array of tiles. Oops. I'll call them ends for neighbors. And if diag_OK equals false, then ends is equal to a new array of 4 tiles, like so. Else, ends equal to a new array of 8 tiles. Tile order is north, east, south, west. Right, we'll go clockwise. Here, tile order is going to be northeast, southwest, northeast, southeast, southwest, northwest. Because if we do that way, And I sort of hate having to do this magic-y kind of bit. There might be a better way to do this later on that's more clear, but let's just move on for now. So we loop through. We basically are going to do very similarly to our furniture sprite controller, and we're going to manually grab the appropriate sprites. We do have a reference to the world, right? Yeah. So this is a potential neighbor. Here, we'll call it N. Potential neighbor. And we're going to get a tile here. This is to our north, because north is positive y. Yes, that is true. If N, actually, we don't have to do a check. We can just say tile, or sorry, N's 0 is equal to N. Now, N might be null. Could return null, but that's okay. You know? Could be null, but that's okay. So there's probably, you know, a better or differently optimized way to do this, but this is, you know, this is going to be fine. There we go. So we want east, south, and west. Boom. So this is going to be the case no matter what, if we have diagonals or not. And then if diagonal okay, and I'm going to make it explicit with equal true, just to make it very clear what's going on there. Then we get another block over here, which is 4, 5, 6, 7. And here we're going northeast. Then we go southeast. Then we go southwest. And finally we go northwest over here. And then we return the neighbors, the neighbor array. Now, calculating this isn't so bad. You know, it's actually very quick. Until you do it for 10,000 tiles. Well, okay, it's not going to be quite 10,000 tiles because we're only creating a node here for every walkable tile, right, as opposed to every single tile in the game. But doing that and then having to do that every time we regenerate the graph could be a little bit annoying. We could cache this, right? Internally, tile could keep track of what its neighbors are, already have an array ready to go to regenerate. The only gotcha is that if our neighbors change, if a tile changes, it's got to regenerate its neighbors, like its own like array of who my neighbors are, plus its neighbors' array. But that wouldn't be too bad. That would actually be pretty damn easy. I guess the only difference is if sometimes we want diagonals and sometimes we don't. Let's figure out that optimization later. Almost certainly we're going to want to cache this stuff later on, but for now it's okay. So this is just going to return the neighbors, and probably there's a better, cleaner way to do it. I'm sure someone in the comment will give us a great new algorithm for that, so I'll take we'll hold on for that. But for now, we'll do this. Later on, there'll definitely have to be some sort of caching. That's going to be good. Okay, so now back over here. So we have in our nodes dictionary, we have a list of all tiles that are walkable in the world, as well as with an associated node. So now we're going to loop through all of those tiles in here. And so we've got the tile. We can also get the node. I guess I could have grabbed it as a pair, but that's going to be fine. So we're going to go path node tile n is equal to nodes t. Okay, there's a way to make this a little bit better, but let's go on ahead for now. Get a list of neighbors for the tiles. So that's okay. We can do that. Tile array ends, or maybe neighbors. Spell it out this time around. What the hell? Let's be inconsistent. Tile.get neighbors. And for this, for our pathfinding, for our movement, diagonals are okay. Note, some of the array spots could be null. In fact, you know, if we're building on an edge, that is very, very, very likely. So, is a neighbor walkable? So, for each, actually, let's do a for loop here. For I in neighbors dot was it length for this one? I hate that it's like length for an array and count for a generic data type. But, you know, I'm so inconsistent in my code, who am I going to yell at? Right, so we're going to loop through there. So we're going to say if neighbors I not equals null, because it could be null, and neighbors I dot movement cost is greater than 0. So the neighbor exists and is walkable. So create an edge. So we are going to create a new tile edge, path edge of type tile, E. It's going to be a new tile edge. So E needs two things. It needs to know its cost, which is fine. We've got that information. This is the cost to enter this neighboring tile. And E.node, this is the end node, is going to be equal to nodes for this neighbor. Because neighbors I is a tile, but we have a dictionary that maps from tiles to nodes, which is going to be that. And again, there's probably a way to make this more optimal. We'll figure this out later on. But we've created an edge here, which is great. And then we have to add this edge to our node. But I was hoping to just use an array here instead of a list. We could make this a list and feed it in there. List is a little bit of extra memory overhead. I think we're probably okay if first we make a list. List of path edge of type tile edges equals new, equals new, like that. So we've created an edge here. We're going to add it to this edge list. And then once we're done looping through all the neighbors, we can go and say our node.edges is equal to the edges.toArray. So we'll convert this list to an array, which should mostly happen auto-magically because internally lists are implemented as an array. I guess the only thing is this might go and trim the array down to the appropriate size. I'm not sure, but we're going to convert it to an array and just keep that as opposed to the list because we really don't need to work with the list that much. Is this a win or not? I'm not sure, but we'll move on. Okay, so neighbor exists and is walkable, so create an edge. Add the edge to our temporary and growable list. I mean, I suppose what we could have done, since in our implementation we know that the edges, the maximum number of neighbors that a node will have is 8. I could have just initialized the node's edges array to 8, and could just be partially empty or something. But I don't know. This is fine. So there we go. So at this point we should, assuming we haven't made any syntax errors, which we're going to find out soon, and assuming we haven't made any logic errors, which we're going to find out in about 16 episodes and be very confused about, this will now create a graph of our world. Now, we're not actually calling this yet, so we should do that. Over in, where is it? Build mode controller. That's where I have the button for do pathfinding test. Okay, so on the screen over here, see if we have any, nope, no syntax errors. Of course, those would have highlighted in red. Over here, I have a button, which creates our little mappy bit over here. So after the world gets populated with our pathfinding test environment, let's go ahead right here. This is just for a test. It's not going to stick around. It's kind of a dumb place to put things, but where else are we going to do a test? This is fine. We are going to create a new instance of path tile graph. And we have to feed it in a world, which we've got over here. And we tell it what the world is, and we say, hey, please create a graph of the world for us. Now, we don't have much in the way of debug information right now. I could turn on the stepper, although stepping through this is going to be a lot of loops, which is tedious. Let's do a run first and see, if things explode. Maybe we have an infinite loop somewhere. I'm not sure. Let's hit play and see what happens. Well, nothing's going to happen on play, not until I hit the button. Well, no code errors. I don't believe that I did it right the first time because it seems very improbable, if not impossible. Well, I guess it's not technically impossible. But in theory, when we hit that button And this runs, which calls the constructor, which is what this thing is here. We create one node for every tile that is technically possible to walk on. Then we loop through all those nodes, check all their neighbors, and for each of the walkable neighbors, we create an edge. Note, we don't create the reverse edge at this point. We sort of could if we then took things out of the array, but no, I think it's better that it just loops through, creates a one-way edge, and then when we loop and hit the next node, it creates the second direction of the edge, and that's perfectly fine. All right. Great. We still don't know. I wonder if there's a way to quickly visualize any of these things. Well, we could probably do something like, let's add some debug information. Debug.log, just as a sanity check. Created nodes.count. Nodes. And for debugging, let's go int edge count equals 0, edge count plus plus, and created edge count edges. Created 345 nodes and 2,200 edges. 335 nodes? That sounds vaguely right-ish. What is the square root of 345 is 18. I think this is about a 20 by 20 square. And some of the tiles are unwritable. It sounds about right. Just as a ballpark kind of figure. I still fully expect that we completely cocked something up somewhere, but for now, I guess we're okay. We could do some sort of neat debugging interface, where if we mouse over a tile, maybe it can show like connected edges or something. That would probably be really handy, although we'd spend like 3 or 4 episodes, well, maybe not quite that much, but at least a full episode just making this debug mode, which may or may not be worthwhile. Maybe it's the sort of thing I'll do between episodes, just for later, assuming we run into any problems. But I guess for now, we'll get started with the pathfinding, because presumably at this point, so we have a graph. So right now, we create a graph over here. It goes away at the end of the function, but that's all right. So next thing we want to do is, well, actually, we might want to keep it. We create the graph. I mean, really, this should always be a graph. It shouldn't get created here. This graph should get regenerated anytime the world changes. Or maybe more accurately, instead of saying the graph should be regenerated every time the world changes, the graph should get destroyed when the world changes, and then it'll get recreated the next time we have to do some pathfinding info. That's probably the best way to do it. All right. So where does the tile graph belong? I think it's possible the world should have a reference to it, at least for now. That's probably the best way to do things. Right? So the world itself, over here, has our list of tiles and characters. So why shouldn't it also have a tile graph? Do I want to call it tile graph? Maybe pathfinding graph? I guess tile graph is fine. The pathfinding graph used to navigate our world map. So we'll have a reference to it there. So build mode, the build mode controller is just going to keep the reference to, it's just going to have this button to make our pathfinding world in case we want it for debugging. But the world itself will keep track of the tile graph, because the world itself already listens for whenever a tile changes. All right, we have a callback here. I'm pretty sure. Where's my Hey, where's my list of functions over here? View paths, document outline. On tile changed. So, gets called whenever any tile changes. Now, I don't think that's true about if a furniture gets created. We have a place furniture function over here. All right, so what we're going to do is we'll make a function. I'll make it public because why not? Validate tile graph. This should be called whenever a change to the world means that our old pathfinding info is invalid. Right, so whenever we build or destroy a wall or put a piece of furniture down, like do something that affects how you can navigate the world, this should be called, and all it's going to do is it's going to set tile graph to null. That's it. And then assuming there's no reference to it anywhere else, it'll just become, it'll get garbage collected. So on tile changed. So if any tile gets changed, we invalidate the tile graph, and also if a piece of furniture gets placed, which is here, we're going to do that. So after all the callbacks get created, because, you know, who knows, other kind of effects might happen there, we invalidate the tile graph, just set it to null, and that's going to be okay. So where do we create the tile graph? Well, it's really going to be when we need to do some pathfinding, right? So our character, for example, wants to go from point A to point B. And so it's going to make a request to the pathfinding system, our A-star pathfinding system. It's going to say, listen, pathfinding system, I am at this coordinate. I would like to go to this coordinate. And that pathfinding system will use the graph of the world. And if the tile graph is null, then it's going to generate the tile graph at that point. Or at least that's the thinking that I'm thinking. We'll see exactly how that goes. But let's say, create a new function over here, a new class. We'll call it path A-star. So this is going to be a class like this. It's going to have a public constructor. Yeah, public A-star. And I think all it's going to do is going to say world and world tile start tile end. So you construct this, you give it the world, you tell it where you want to start from, where you want to end. It's going to generate a path, and then it's going to have some sort of list, generic, something like list tile path, and something like some sort of public function called like get next tile or something of this nature. We'll almost certainly make some tweaks over here. But so basically you create the path. You say, listen, here's the world. Here's where I want to start. Here's where I want to go. And then our character will keep asking what the next tile is in the path. So right here, it'll generate the whole path from point A to point B. And here we'll ask it, you know, hey, give me the next tile when you're at, you know, if you've finished the entire path queue. This is sort of, it's sort of the queue. Maybe that might be the better way to word it. In fact, we might even use a queue because logically, this is a queue. You know, you only take things off the top. And generating it is basically just adding things, although every now and again you get in a situation where things sort of get generated in the reverse order. But logically it'd be this, and logically it would be something like path.dq. Right? It's this sort of thing is conceptually the way it works. We're not sure exactly what the internal implementation will be until we basically finish this and we figure out exactly what we need. But it's going to be that sort of thing. So our character on update, right now, the character knows what its destination is. It's got distance. Where is it? We have a destination tile. Okay? And right now, this is our endpoint, our destination tile. But that's not what I want. I want destination tile to actually be just the next step in the path. So basically, whenever we get to our destination, which is here, we have reached our destination. To do, get the next destination, or get the next tile from the pathfinding system. If there are no more tiles, then we have truly reached our destination. You dig? So it's going to be, this is the sort of thing that we're going for. So we don't know exactly how we're going to pull the data out quite yet. We are going to start to work on the actual pathfinding system over here. We actually may have to put a cut in here. It's a bit long. I will tell you this. We are mostly going to be bringing up the Wikipedia page for the A-star search algorithm. And it's got a bit of pseudocode in here. You can take a look at that right away. What we're going to do is we're going to use this pseudocode here, and we're just going to basically convert this to C#. There are already C#, like very nice generic algorithms for A-star implemented in C# that we could use. A lot of them are really, really optimal, really, really good. I'm going to go and implement this because I don't think we've done a video. No, we haven't. We haven't done a video where we've implemented A-star. I have done a video where we have implemented the Dijkstra's algorithm over here. And in fact, if you look at the history of this page, you should see somewhere in here. Oh, it might be too old. Oh, it must be older than that. You should actually see a bunch of changes that I did, because the last time we did it, I found out, there we go, I found out there were some bugs on the page for the Dijkstra's algorithm. Because someone had made some changes to it at some point, which had broken a bunch of references, and some of it wasn't clear, so I made a couple of tweaks here, which I was pretty happy about. So, anyway, I liked it. Me contributing. So, Dijkstra is really simple to implement, but it's not quite as fast. We can actually get a nice little side-by-side comparison of the two. How am I going to do this? If I pull this off here, and do this, and let me take this window and shrink it down, and then hit refresh, put them side by side. There we go. So you can compare. This is A-star over here, and this is Dijkstra's over here. And A-star uses an extra little heuristic to try to hint which way to go. Dijkstra's, I believe, is always perfect. It will never somehow screw up and give you a slightly less optimal variant. It's technically feasible, I think, to construct a sort of example in A-star, where technically the path you get is not actually the fastest path, but it calculates so much faster, and it's very unlikely that it will find an unoptimal path. It's not going to be unoptimal, it's just going to be slightly less than the ideal, but it calculates so much faster. In fact, it can almost calculate its route twice in the time it took Dijkstra's to run one time. The advantage of Dijkstra's is it's sick easy to implement. The pseudocode for A-star is a little bit longer. It also requires that we have a priority queue, which is a type of data structure, which in the version of C# that ships with Unity, there's not a generic one implemented, as far as I can tell. Actually, I don't even know if there's like a C# library that is like just shipped by default that includes a priority queue implementation, which is too bad. It's a sort of a priority queue is what, like a min heap kind of thing. In any case, we do have a good implementation of that already in the project. So some things I'm going to code from scratch, some things I'm not, but we are going to go ahead and implement A-star, even though there's probably going to be a faster, more optimal, and less memory intensive version of it already out there. It's going to be a good exercise, but we're going to do that next time. But if you want to work ahead, this is basically what we're going to be copying from. It's not very hard, as long as you can read pseudocode. See you next time, folks. Bye-bye. thank you very much to all our January supporters over at patreon.com/Will18Creates, and these mic check supporters. We've got Alexander Gutler, Andre Odendal, Neil Blakely Milner, Speedy Savant, Valiant Cake Fiend, Aaron Toyson, Marius Field Vold, Disco Geek, Ole Peter Talgo, Julian Auger Lafont, or Auger Lafont, I should say, Steven Stagger, Michael McClintock, Kale the Quick, Drazion, Wes Oldenbeving, Craig Mortel, Nail or Nale, I don't know, Vikstrom, and Andrew Henninger, and everyone who has watched, shared, favorited, and subscribed to these videos, and left comments as well. You guys really keep things going. Thank you very much for watching.